Imagine you are standing on a world at the far outer edge of a spiral galaxy. Behind you, tens of thousands of light years away, is the bright crowded middle where nearly all the stars are. Around you there is almost nothing. Thin gas, a scattering of distant suns, and a great deal of empty space. By every rule we have ever tested, you should be crawling. The pull holding you in orbit comes from all that mass back there in the centre, and it has weakened enormously across that distance. You should be moving slowly, the way Neptune moves slowly compared to Mercury. You're not moving slowly. You're moving just as fast as the stars near the middle, and so is everything else out here, and this is true in every galaxy anyone has ever measured carefully enough to check. Something is holding you, and it is not anything you can see. So what is out here with you? And is it possible that the answer has been photographed, catalogued, and sitting in plain sight the entire time? Get cozy and settle in. Subscribe if you have not, and stick around, because before any of this can make sense, you have to see the one step in Einstein's reasoning that almost nobody ever checks. Let's begin. Part 1. The thing that has never been found. There is a machine, right now, a kilometre underneath a mountain, and its entire job is to wait. It sits in a chamber cut out of rock, and above it there is enough stone to stop almost everything the universe throws at the surface of the Earth. Cosmic rays do not get down there. Stray radiation from the rock itself has been shielded layer by layer, with lead and with copper and with water. At the centre of all of that, in a tank the size of a small car, there is liquid xenon, held just above the temperature where it would freeze solid. The xenon is very still, the chamber is very cold, and the whole apparatus, which cost hundreds of millions of dollars and took a decade to build, has been assembled for one purpose: to notice if a single atomic nucleus in that tank ever gets knocked sideways by something invisible. Imagine you could stand in that chamber. It would be dark, and it would be quiet in a way that is difficult to arrange anywhere on the surface of this planet. Not the quiet of a still night, which is full of small sounds, but the quiet of a place where almost nothing arrives. You would be standing next to an instrument built to detect an absence, and according to our best current model of what the universe is made of, at this exact moment, something like 100,000 invisible particles are passing through every square centimetre of your body, every second, through your hands, through the tank, through the mountain above you, and out the other side of the Earth without slowing down. The detector has been running for years. It has recorded nothing. That is not one detector either. That is a whole generation of them, in Italy and in South Dakota and in China and under a mountain in Japan, each one more sensitive than the last, each one built by people who had every reason to believe they were about to find something. The searches have improved in sensitivity by many orders of magnitude over 4 decades. The Large Hadron Collider has run dedicated searches. Space telescopes have looked for the light that would be produced if these particles ever ran into each other, and the collected result of all of that effort so far is a very long and very precise list of places where the thing is not. So let us start with a simple question, and let us be honest that it is a strange one to have to ask. Where would you hide a quarter of the universe? Because that is the size of the claim, not a rounding error, not a small correction to a mostly complete picture. On the standard model of cosmology, the model that appears in every textbook and underlies almost every calculation working astronomers make, the universe breaks down roughly like this. About 68% of it is dark energy, which is whatever is causing the expansion of space to accelerate. About 27% of it is dark matter, and everything else, every star you have ever seen, every planet, every grain of dust in every nebula, every atom in your body and in the chair you're sitting in, and in the air moving in and out of your lungs, everything that has ever emitted or absorbed a single particle of light in the whole history of the universe is the remaining 5%. 5%. That is the fraction of reality that is made of the kind of stuff we are made of. Now, that is an extraordinary claim, and it did not come from nowhere. It came from measuring how galaxies turn. Here is the observation, and it is worth going slowly through it, because everything in this entire story depends on it, and almost nobody has ever shown what it actually looks like. Take our own solar system first, because the solar system is the place where we learned how gravity behaves. Mercury goes around the Sun very quickly, about 47 kilometres every second. Earth is slower, about 30. Jupiter, much further out, is down to 13. Neptune, out at the edge of the planetary system, is crawling along at about 5.5 kilometres per second. The further out you go, the slower things move, and that is not a coincidence or a quirk of how the solar system formed. It falls directly out of Newton's law of gravity. The sun's pull weakens with distance. It falls off as 1 over the distance squared, and an object further out needs less speed to stay in orbit, because there is less to hold it. Plot orbital speed against distance from the sun, and you get a curve that starts high and comes down. That shape has a name. It is called a Keplerian fall-off, and it is one of the most thoroughly confirmed relationships in the history of science. We navigate spacecraft with it. We have never seen it fail inside the solar system. Not once. Not by anything that anybody has been able to measure. Now do the same thing with a galaxy. A spiral galaxy is, in the crudest possible description, a great flattened wheel of stars turning around a bright, dense middle. Most of the visible light, most of the stars, most of the gas, is packed into the central regions. Out toward the rim, the disk thins dramatically. There are fewer stars, more space between them, less of everything. So if gravity behaves the way it behaves in the solar system, the stars near the edge of a galaxy should be moving slowly. Whatever mass is holding them is mostly back there in the middle, far away, and its pull should have fallen off badly by the time you get out to the rim. The rotation curve should come down, the way the solar system's does. It does not come down. It goes flat. You measure the speed of the gas and the stars as you move outward from the centre of a spiral galaxy, and the speed climbs as you would expect through the inner regions, and then it levels off, and then it just stays there. Kilometre after kilometre, thousand of light years after thousand of light years, right out past the last star you can see, out into regions where the visible galaxy has essentially ended, and there is nothing but thin gas. The rotation speed does not drop. Sometimes the curve stays flat for tens of thousands of light years, beyond the point where the light runs out. That should not be possible. Objects moving that fast, that far out, with that little visible mass inside their orbits, should have been flung off into intergalactic space a long time ago. The galaxy does not have enough gravity to hold on to them, and yet there they are, holding together, turning, in galaxy after galaxy after galaxy, in every spiral we have ever measured well enough to check. So something is wrong. And when a measurement disagrees with a law, there are exactly 2 things you can do about it. You can decide that the law is right and the inventory is wrong, that there is more mass out there than you can see, and you simply have not accounted for all of it. Or you can decide that the inventory is right and the law is wrong, that you have counted everything correctly, and the equation you're using to convert mass into gravity is not the correct equation at that scale. Physics chose the first door. It chose it in the 1970s, after the rotation curve measurements became too good and too numerous to explain away, and it has been walking through that door ever since. The missing gravity implies missing mass. The missing mass must be something that does not give off light, or absorb it, or reflect it, or interact with ordinary matter in any way we could easily notice, because otherwise we would have seen it long ago. It has to be spread out in a great roughly spherical cloud, a halo, surrounding each galaxy, extending far past the visible disk, quietly doing the gravitational work that the visible stars cannot do. And there has to be a lot of it, roughly 5 times as much of it, by mass, as there is of everything visible. That is dark matter. And I want to be very clear about something before we go any further, because it matters for everything that follows. The people who proposed it were not being lazy, and they were not being credulous. Proposing an unseen mass to explain an orbital anomaly is one of the oldest and most successful moves in the history of astronomy. In the 1840s, Uranus was not orbiting the way Newton's laws said it should. 2 mathematicians, working independently, calculated where an unseen planet would have to be to produce the discrepancy. Astronomers pointed a telescope at that spot, and Neptune was there, within a degree of the prediction. That is the single most impressive prediction in the history of celestial mechanics, and it was made by exactly this reasoning. The law is right, so there must be something out there we have not seen. So when the rotation curves came in flat, the field did the thing that had worked before. It looked for the planet, and that search has now been running for over 40 years. There is a difference, though, and it is worth sitting with. When they went looking for Neptune, they found Neptune, and they found it almost immediately. Here, decade after decade, the searches have come back empty, and each empty result has required the theory to retreat a little. The particle must be lighter than we thought, or heavier, or interact more weakly than we thought, or not interact at all except through gravity. Every non-detection narrows the space where the thing could be hiding, and the space has been narrowed a great deal. There is also a second thing worth noticing, and this one is easy to miss. In the 1840s, the unexplained wobble in the orbit of Uranus was solved by finding a new planet. But there was a second unexplained orbital anomaly at the time, and it was in the orbit of Mercury, a small extra advance in the point of its closest approach to the Sun, about 43 arcseconds per century, that Newton's laws could not account for. Astronomers applied the same reasoning. They proposed an unseen planet closer to the Sun than Mercury, and they named it Vulcan, and people spent decades looking for it. There were sightings, there were papers, there was for a while a real scientific consensus that Vulcan existed. Vulcan does not exist. There was never a planet there. The reason Mercury's orbit did not fit was that Newton's law of gravity was not the final word, and in 1915 Einstein produced a theory that got the 43 arcseconds exactly right, with no extra planets at all. Same reasoning, same field, roughly the same decades. One time it was a missing object, the other time it was a missing law, and there was no way from the outside to tell which kind of problem you had until somebody solved it. So keep both of those in your mind, because this whole video sits in the space between them. Every time a measurement disagrees with the equations, you are standing in front of two doors, and they look identical from the front, now. There is a physicist who has spent his entire working life, and I mean his entire working life, since 1972, arguing that in this particular case the field has been standing in front of the wrong door. His name is Philip Mannheim, and he is a theoretical particle physicist at the University of Connecticut. He is not an astrophysicist. He does not describe himself as a relativist. He came at this from the direction of particle physics and symmetry, which turns out to matter enormously, because it means he was not trained to take the standard picture of gravity as a finished object, and his claim is not the one you would expect. He is not saying dark matter is a hoax. He is not saying the astronomers measured the rotation curves wrong. He thinks the data are excellent, and he has spent decades fitting them. He's saying something much stranger and I think much harder to shake off once you have properly understood it. He's saying the missing mass is not missing. He's saying it has been in the sky the whole time, photographed, catalogued, sitting in survey images on hard drives at observatories all over the world. Not dark at all, not exotic, not undiscovered, just ordinary visible matter, the same kind of matter as everything else, in a place nobody thought to look because of a decision that was made about a differential equation more than 100 years ago. His phrase for it is that the missing mass has been hiding in plain sight. Now, that is either a very serious statement or a very slippery one, and I'm not going to tell you which yet. To even understand what he means by it, you have to understand something about how general relativity was actually built, not the version in the popular accounts, where a genius has a vision about falling elevators and hands the universe a finished theory, but the actual sequence of steps, in order, including the one step that Mannheim says nobody checks, and that step is not where you think it is. Part 2. The two problems, not one. We tend to talk about general relativity as if it were a single idea, arriving all at once, the way a building arrives when you take the scaffolding down. That is not what happened. Einstein was working on two separate problems, and the solutions to those two problems are logically independent of each other, and the fact that they were solved by the same person in the same decade and published under the same name has, according to Mannheim, obscured something important for 100 years. Let me show you both problems, because the first one is beautiful and the second one is where the argument lives. Start in 1905 with special relativity. Einstein was looking at two pieces of physics that did not agree. On one side there was Newton's mechanics, which had a particular set of symmetries, a particular set of ways you could change your point of view without changing the physics. On the other side there was Maxwell's theory of electricity and magnetism, which had a different set. Two of the most successful theories in existence, and they disagreed about something as basic as what happens when you change your speed. You can see the problem in Newton's second law without any mathematics at all. Newton says force equals mass times acceleration. Push on something, it accelerates. Keep pushing, it keeps accelerating. There is nothing in that statement that ever stops. Push on a spacecraft for long enough with a steady force, and according to Newton, it will eventually be moving faster than light, and then faster than that, and there is no point at which the equation objects. Maxwell's theory says that cannot happen. So something had to change, and what Einstein changed was the underlying symmetry. He replaced the old assumption about how observers moving at different speeds relate to each other with a new one, which we now call Lorentz invariance. Under the new rule, the physics is the same for any observer moving at a constant velocity, no matter how fast, right up to but never reaching the speed of light. That is special relativity, and notice what it is. It is a statement about symmetry. It is not a specific equation for a specific force. It is a rule that says any correct equation, whatever it turns out to be, has to look the same to observers in uniform motion. This distinction is going to matter enormously in about 10 minutes, so hold on to it. Now, two things were missing. The first is that observers do not only move at constant velocity, they also accelerate, they turn, they rotate. You are right now sitting on a rotating planet going around a star in a galaxy that is itself turning. So what happens to the laws of physics when the person writing them down is not moving uniformly? Here is where it gets interesting, and here is where Einstein does the thing that I think is his most underrated piece of work. Take Newton's second law and write it out in a coordinate system that is rotating or accelerating, and extra terms appear. You have felt those extra terms. They are the reason you get pushed sideways in a turning car, the reason a merry-go-round throws you outward, the reason weather systems curl. In classical physics, these are called fictitious forces, and the word fictitious is doing a lot of work because from inside the rotating system they feel entirely real. Ernst Mach was troubled by this, and his response was one of the great intuitions in the history of physics. He suggested that these extra terms were not fictitious at all, that they came from an interaction with the distant matter of the universe, with the stars. Spin a bucket of water, and the surface curves. Mach asked, curves relative to what? And his answer was, relative to everything else there is. Remember that answer. It goes away for 100 years and then it comes back in the middle of this story with the force of a returning ghost. What Einstein did was to find a way to write the law of motion so that it does not change when the observer accelerates or rotates. The resulting equation is called the geodesic equation, and I am not going to make you look at it, but I do want you to understand its shape because its shape is the whole trick. It has two pieces added together. One piece is the acceleration, how the object's position is changing and changing again. The other piece is built out of something called the connection, which measures how the coordinate grid itself twists and stretches from point to point. And here is the elegant part. Neither of those two pieces on its own behaves properly when you change coordinates. Each one, taken alone, changes into something else. But the specific combination, the acceleration plus the connection, with the connection appearing exactly once and not twice and not half a time, that specific combination transforms correctly. Change your coordinate system however you like, and if the combination was 0 before, it is 0 afterward. Only one weighting works. Any other weighting falls apart. Now, out of that single structural fact, two enormous things drop out for free. The first one you have known about since you were a child, and you have probably never been told where it comes from. The same mass multiplies that entire expression, the acceleration piece and the connection piece together, because they are locked into one combination. Which means the mass that resists being pushed, what physicists call inertial mass, has to be exactly the same number as the mass that responds to gravity, the gravitational mass. Not approximately the same. Exactly. Because if they were different numbers, the combination would come apart, and the equation would stop working when you change coordinates. That is the equivalence principle, and it is the reason a hammer and a feather hit the lunar surface at the same instant, which the crew of Apollo 15 filmed so that you would not have to take it on faith. It is why you feel weightless in free fall. There is no known reason in Newton's physics why those two masses should be the same number. It is a coincidence that Newton simply wrote down and moved past. In Einstein's structure, it is not coincidence at all. It is forced. The second thing that drops out is subtler. At any single point you choose, you can always find a coordinate system in which that connection term becomes 0. It will not stay 0 at the point next door, but right there, at that one point, you can make it vanish. And if the connection is what gravity is made of, then you have just shown that gravity, at any single point, is equivalent to an acceleration, which is the falling elevator. Step off a ledge and for as long as you're falling, gravity has locally disappeared from your world. Astronauts on the space station are not beyond Earth's gravity. They are extremely inside it, being pulled almost as hard as you are. They are simply falling continuously, and so the connection term has been transformed away for them. Now here is the question that turns this from a piece of mathematics into a theory of the universe. If you can make gravity disappear by choosing coordinates, how do you ever know whether it was real? Because there is obviously a difference between the two cases. A person in free fall feels nothing. A person strapped to a spinning flywheel feels a great deal, and if the flywheel spins fast enough it will do them serious damage. Both situations can be described with connection terms. One of them is a genuine physical thing happening, and one of them is an artifact of how you set up your grid. What separates them? The answer is that you can change the first derivative of the metric, that is what transforming the connection away means, without changing the second derivative, and the second derivative gives you a quantity called the Riemann tensor, and a tensor has a very specific mathematical property. If it is not zero, there is no coordinate transformation anywhere that can make it zero. It is not an artifact. It cannot be argued away by changing your point of view. It is there for everyone. So Einstein arrived at the following picture, and it is worth stating carefully because every single word of it survives the rest of this video intact. The metric, the thing that tells you distances and durations, is the gravitational field. The connection built from it tells you how things move. And when the Riemann tensor built from it is not zero, there is real curvature there, and real gravity, and nobody can transform it away. I want to give that discovery its due for a moment, because Mannheim, who has spent 50 years arguing about the parts of general relativity he thinks are wrong, describes this particular part as one of the most surprising discoveries in human history, and says that after knowing about it for many decades he is still surprised by it. What Einstein did was take a piece of mathematical bookkeeping, a set of numbers that tell you how to measure the length of a line in a coordinate system, something you would use to convert between rectangular coordinates and polar coordinates on a flat sheet of paper, something entirely mundane, and identify it as gravity. The bookkeeping and the force turned out to be the same object. There is no obvious reason on earth why that should have been true, and here is a distinction that almost every popular account skips, and it will matter shortly. Everything I have just described is still true in completely flat, empty, gravity-free space. Switch from rectangular coordinates to polar coordinates on a flat piece of paper, and connection terms appear immediately. That does not curve the paper. It does not summon a gravitational field. It is purely a property of the coordinates you chose. So all of this machinery, the geodesic, the connection, the equivalence of gravity and acceleration, is in place before gravity has entered the picture at all. Which brings us to the problem. You now know that the metric is the gravitational field. You know the connection depends on the metric, and the Riemann tensor depends on the metric. What you do not know is what the metric actually is in any given situation. Think about what that means practically. Suppose you want to know how a planet moves near a star. The geodesic equation tells you how a particle responds to a gravitational field. Terrific. But it does not tell you what field the star produces. For that you need a second, entirely separate equation. An equation that takes matter as input and hands you geometry as output. Something that says, here is a star of this mass, and therefore here is how space-time is shaped around it. Einstein needed to write that equation down, and the way he wrote it down is the second problem, and it is where Mannheim's entire life's work lives, because that step, unlike everything I have just walked you through, was not forced. Part 3. Where the field equations came from. So Einstein needs an equation that turns matter into geometry, and he asks himself a very sensible question. What did the old theory say? Newton's law of gravity, written in the form physicists prefer, is something called the Poisson equation. In words, and I'm going to keep this in words all the way through because the symbols will not help you here. It says that the way the gravitational pull changes as you move around a point is determined by how much matter is packed in at that point. It is a local statement. Tell me the density of matter everywhere, and this equation tells me the gravitational potential everywhere. Solve it for a single compact object like a star, and out comes the potential falling off as 1 over the distance. The inverse square force law, Newton's gravity, the thing that has been tested for 300 years and never once failed inside the solar system. And it has a particular structure. It is second order, meaning it involves the rate of change of the potential, and it stops there. 2 derivatives, no more. Now Einstein notices something. The Riemann tensor, the thing that measures real curvature, is also built out of two derivatives of the metric. So there is an obvious correspondence available. If the metric is the gravitational field, and the old law of gravity is a second-order equation for the gravitational field, then the natural thing to do is write a second-order equation for the metric. Take Newton's Poisson equation and ask what it looks like when you write it in a way that works in any coordinate system, accelerating or not. Do that carefully, and you get the Einstein field equations, matter and energy on one side, curvature on the other, and the famous summary that John Wheeler gave decades later. Matter tells space-time how to curve, and space-time tells matter how to move, and then you test it. And it works, twice in the most public way possible. The first test was already sitting on the table. Mercury's orbit has that stubborn extra 43 arc-seconds per century in the advance of its closest approach to the Sun, the anomaly that had people hunting for a planet named Vulcan for decades. Einstein put Mercury into his new equations and got 43 arc-seconds, not approximately. He's reported to have had heart palpitations, and the reason that result was so devastating is that he did not tune anything to produce it. There was no adjustable knob. The number came out. The second test was the bending of starlight, and this one was theatre. Light passing close to the Sun should be deflected, and Einstein's theory predicted a specific deflection, twice the amount you would naively get by treating light as a falling particle in Newton's theory. In 1919, expeditions went to Brazil and to an island off West Africa to photograph a total solar eclipse and measure the apparent positions of stars near the darkened Sun. The measurement favoured Einstein. It made the front page of newspapers all over the world. It made Einstein, essentially overnight, the most famous scientist alive, which, as we will see much later, turned out to have consequences of its own. So by 1919, gravity is solved. That is the story, and I want to be clear that it is a good story and mostly a true one. Here is Mannheim's objection, and it is not an objection to any of those results. It is an objection to the direction the reasoning ran. Look again at how the field equations were built. Einstein started from the Poisson equation. Where did the Poisson equation come from? From Newton. Where did Newton's inverse square law come from? From 300 years of watching the solar system. That is it. That is the entire pedigree. The inverse square law is an empirical fact about a region of space a few tens of astronomical units across, extracted from watching 6 planets and a moon. So general relativity did not derive Newton's law of gravity. It found the generalization of Newton's law of gravity that also works in accelerating coordinate systems. Newton was an input. Newton went in the front of the machine and came out the back, in a more sophisticated form, with a correction term attached that turned out to explain Mercury. Mannheim's word for this is phenomenology. He does not say it as an insult. Phenomenology is a completely respectable activity, and most of physics is made of it. But there is a distinction he is drawing, and it is sharp. Everything I described in the last part, general coordinate invariance, the equivalence principle, the metric as the gravitational field, the Riemann tensor as the marker of genuine curvature, all of that is generic. It follows from requiring that physics not depend on your point of view. It has no free choices in it. Mannheim's position is that any theory of gravity whatsoever must contain every one of those ingredients, and his own theory contains all of them. The field equations are not generic. They are a specific choice, constructed to do a specific job, and the job was reproduce Newton. Now I can hear the obvious objection, because it is the right objection, and when it was put to Mannheim directly he agreed with it immediately. What is wrong with knowing where you want to end up? We know Newton works. Any new theory has to reduce to Newton in the regime where Newton has been confirmed, or the new theory is wrong. Building a theory to land in the right place sounds less like a flaw and more like basic competence, and that is correct. That is good physics. The point is not that Einstein did something illegitimate. The point is that this step sits on a different conceptual footing than the rest of the theory. The equivalence principle is forced. General coordinate invariance is forced. The metric being the gravitational field is a discovery. The field equations are a construction, aimed at a target, and the target was 300 years of observations of one solar system. And here is the consequence, and this is the whole hinge of the argument. Because Einstein wrote the specific equations at the same time as he wrote the generic framework, and because the whole thing worked so spectacularly, Physics came to treat general relativity as a single indivisible object. You cannot touch any part of it. Question the field equations and you are questioning the equivalence principle, questioning Mercury, questioning the eclipse, questioning Einstein. But those are separate claims. Mannheim makes a point about the name itself, which I found genuinely clarifying. Special relativity means invariance under a particular set of transformations. It does not mean any specific equation of motion. Maxwell's equations happen to be Lorentz invariant, and so is the Dirac equation, and so are many things, and special relativity is the rule they all obey rather than any one of them. By the same logic, general relativity ought to mean invariance under general coordinate transformations, with the metric as the gravitational field. That is what the name says. It should not additionally mean, and the gravitational field obeys these particular equations. Those are two different statements that got welded together because one man made both moves in the same decade and both moves worked. There is another way to see that the two halves come apart, and it is a simple one. Even where there is no gravity at all, things accelerate. An electric field will accelerate a charged particle perfectly well in empty space. So the machinery for describing accelerating observers has to work whether or not gravity is present. It is not a gravitational statement. It is a statement about coordinates. Fusing it to a specific gravitational field equation was a historical accident. I want to slow down here, because I think this is the part that is easy to nod along to and hard to actually feel. We are not talking about a mistake. Nothing I have described is an error. Every step Einstein took was reasonable, and the theory that came out of it is one of the most successful pieces of work any human being has ever produced, and it is still passing tests today that nobody in 1915 could have imagined. Gravitational waves from colliding black holes, the timing corrections that let the satellite navigation in your phone work, the direct images of the shadow around a supermassive black hole. General relativity is not in trouble. It is spectacular. What we're talking about is a place in the reasoning where a choice was made, where the choice was justified by data from one particular regime, and where nobody has ever gone back and demonstrated that the choice was the only possible one. And Mannheim's whole career is essentially one long insistence on a single question. If you're going to tell me that the universe is filled to the brim with an invisible substance outweighing everything visible by 5 to 1, then show me the fundamental principle that says the second-order equation, and no other, is the right starting point. Not the fact that it works in the solar system. I know it works in the solar system. The principle. The reason it could not have been otherwise. That principle has never been produced. It is not that somebody produced a bad one. It is that the question is not usually asked. Which brings us to the thing that turns this from a philosophical complaint into an argument with numbers in it. Because it turns out you can ask a very concrete question about that second-order choice. You can ask, if I had made a different choice, what would the difference look like, and where would I be able to see it? The answer is going to be uncomfortably specific, and there is a piece of advice Mannheim gives his students that belongs here, before we go any further, because it is the standard everything that follows has to be measured against. The number of beautiful mathematical theories, he says, exceeds the number of physically relevant ones by an enormous margin. So do not be seduced by the mathematics. Always keep an eye on the data. Nature will tell you what to do, and you cannot proceed without nature. Nature will keep you honest. Remember that. It is going to come back around at the end of this, and it is going to be pointed in a direction you might not expect. Part 4. 1 over r is not unique. Let us do the concrete thing now. Let us actually ask what happens if you make a different choice. The Poisson equation, remember, is second order. 2 derivatives. Solve it for a compact object and you get a potential going as 1 over the distance. Newton. Now write down the fourth order version instead. Same idea, same setup, same matter on the right-hand side, but 4 derivatives instead of 2. What comes out? 2 things come out. You get the 1 over the distance term exactly as before, and you get a second term sitting right next to it that grows linearly with distance. Go further. Write down the 6th order version. Now you get 1 over the distance, and the linear term, and a third term growing as the distance cubed. Sit with what that means for a second, because it is the sort of thing that is completely obvious once you have seen it, and essentially invisible until you do. The inverse square law of gravity is not uniquely tied to a second-order equation. It comes out of the 4th order equation too, and the 6th order equation, and every higher one. Newton's law does not identify which equation you are solving. It is a solution to all of them. What changes as you go up in order is not whether you get Newton, you always get Newton, it is what else you get alongside it. So when Einstein looked at Newton's inverse square law and reasoned backward to a second-order field equation, he was making a choice that the data did not force. The data are compatible with the second-order equation. They are also compatible with the fourth-order equation, and with the sixth, and with an infinite family of others, each of which contains Newton plus something extra. Now, the obvious question, if there could have been extra terms all along, why has nobody ever noticed them? And the answer is the reason nobody spotted this for 100 years, and it is almost embarrassingly simple. Look at what those extra terms do. The Newtonian term falls off with distance. That is the whole character of it. It dies away. The extra terms grow with distance. The linear one grows steadily. The cubic one grows viciously, which means that at short distances the extra terms are nothing. They are so far below the Newtonian term that no instrument could separate them. And the solar system, for all that it feels enormous to us, is short distance. The Earth sits 1 astronomical unit from the Sun, about 150 million kilometres. Neptune is 30 times further out. The whole planetary system spans a few tens of astronomical units. On that scale, a term rising linearly with distance is utterly, hopelessly negligible. It could have been sitting in the equations from the beginning, and every measurement ever made of every planet and every comet and every spacecraft would have come out exactly the same. There is nothing you can observe in the solar system that excludes it. Not because our measurements are poor, they are extraordinary, we track spacecraft to within meters across billions of kilometers, but because the effect is not there to be measured at those distances. You cannot rule out a term by looking where it does nothing. So where does it start doing something? You have to go up in scale, and the next scale up, the next place where gravity is doing structural work in the universe, is the galaxy. And a galaxy is not slightly bigger than a solar system. It is bigger by a factor of 1,000 at minimum, and depending on what you're comparing, a great deal more than that. The Milky Way is roughly 100,000 light-years across. A light-year is about 63,000 astronomical units, so you are jumping from a system spanning tens of astronomical units to one spanning billions of them. That is where a term rising linearly with distance would finally wake up. And now I want you to hold two facts side by side. Fact 1. The field equations of general relativity were constructed by generalizing a law, extracted from solar system observations, and there exists a whole family of alternative equations that agree with every solar system observation while differing at larger scales. Fact 2. The place where gravity appears to fail, the place where we are required to introduce an invisible substance outweighing everything visible by 5 to 1, is the galaxy. Those two facts are about the same boundary. Dark matter is required in precisely and exclusively the regime where the field equations were never derived, never tested, and simply extended by assumption. That is not a proof of anything. I want to be very careful here. It is entirely possible for a theory to be correct outside the regime where it was constructed. That happens constantly, and it is one of the reasons physics works at all. Newton built his gravity from planets, and it turned out to describe the orbits of binary stars he never saw. Maxwell built electromagnetism from laboratory apparatus, and it turned out to describe radio waves nobody had generated yet. Generalizing beyond your data is not a sin. It is the whole point. But there is a difference between a theory succeeding outside the regime it was built in, and a theory failing outside that regime and being rescued by a new ingredient. And the failure and the rescue are both happening at exactly the boundary you would predict if the extension were the problem. Let me put this another way, because I think there is a version of this that lands harder. Suppose you had never heard of dark matter. Suppose someone handed you the following two pieces of information and nothing else. First, gravity has been tested to exquisite precision across a region roughly 10 astronomical units in scale, and the equation used to describe it was reverse engineered from those tests. Second, when the same equation is applied to a region 1 billion times larger, it comes up short by a factor of 5, uniformly, in every such region anyone has examined. What would your first hypothesis be? I do not think most people's first instinct, given only those two facts, would be that 80% of the matter in the universe is a substance nobody has ever detected. I think most people's first instinct would be that the equation might not extrapolate. Now, the field did not choose the extrapolation lightly, and there are excellent reasons for the choice that I will get to properly, because dark matter is not just a rotation curve patch. It does real explanatory work in the formation of structure, and in the pattern of the early universe's radiation, and any honest account of this has to say so. We will come to all of that. But at the level of the initial move, in the 1970s when the rotation curves came in flat, the assumption that the equation held perfectly across a billion-fold change in scale was not examined. It was inherited. And there is one more turn of the screw, because it is not as though the extra terms are exotic. They are not something Mannheim dreamed up to fit galaxies. They are what you get automatically for free, without asking, if you write down a gravitational equation with 4 derivatives instead of 2. They are the generic case. The second-order equation is the special case, the one where all the extra structure has been set to 0 by hand. We tend to think of Newtonian gravity as the simple, natural thing, and any deviation from it as an elaborate addition. In this framing, it is the other way around. A potential that goes purely as 1 over the distance, with nothing else beside it, all the way out to infinity, on every scale in the universe, is an extremely strong assumption. Something has to enforce it, and nobody has ever said what. There is a consequence of that assumption that Mannheim points to, and once you see it, you cannot unsee it, because it explains the entire shape of the dark matter research program. If the potential really is 1 over the distance and nothing else, then gravity is strictly local in a particular sense. The pull at any point is dominated overwhelmingly by the matter nearest to it, because everything further away has been suppressed by the fall-off. So if you find yourself short of gravity in some region, there is only one place the missing gravity can come from. It has to come from mass in that region. You cannot borrow it from somewhere else, because the somewhere else has been dialed down to nothing by the 1 over the distance, which means that if you assume the inverse square law, and you are short of gravity in a galaxy, you are logically compelled to put unseen matter inside that galaxy, not somewhere else. There. The halo is not really a discovery about the universe. It is a consequence of the fall-off, which was a consequence of the second-order choice. But a linear potential does not fall off. A linear potential grows, and a term that grows with distance can carry influence from very far away into a local calculation. If that term is real, then matter outside the galaxy, matter enormously far outside it, can contribute meaningfully to what is happening inside, and that, though we have not earned it yet, is the shape of the answer. That is where the missing mass is going to turn out to be hiding. Before we get there, though, we have to deal with the obvious question. All of this so far is negative. It says the second-order choice was not forced. It does not say what should replace it. You cannot walk into physics and say your equation might not be unique. Everyone knows that already, and shrugging at Einstein is not a research program. So, is there a principle? Is there something that picks out a particular equation, not because it reproduces an answer we already had, but because the structure of physics demands it? There is. And to find it, we have to leave gravity entirely for a while and go and look at how the other 3 forces of nature actually work. Part 5. Everybody has already modified these equations. Before we go looking for a principle, I want to close off an escape route, because there is a natural response to everything in the last part that goes something like, fine, in principle other equations exist, but in practice you cannot just go changing Einstein's equations, except that everybody already has, including Einstein. In 1917, 2 years after publishing the field equations, Einstein added a term to them. He was trying to describe the universe as a whole, and at the time everyone assumed the universe was static, not expanding, not contracting, simply there. His equations refused to give him that. A universe full of matter under its own gravity wants to collapse. So he added a constant term, the cosmological constant, to hold it open. Then Hubble showed the universe was expanding, and the static universe was not needed, and the constant was dropped. Then, in 1998, 2 teams measuring distant supernovae discovered that the expansion is accelerating, and the constant came back, now interpreted as dark energy, and it has been in the equations ever since. It has had one of the most erratic histories of any quantity in physics, but look at what that history demonstrates structurally. Einstein added a term. He could add it because nothing in the theory forbade it. If the field equations were genuinely unique, if there was some principle fixing their form completely, then you would not be able to add anything, and the question of whether the cosmological constant belongs there would be answerable from the theory itself, rather than from observation. It is not. The theory is comfortable with the constant present and comfortable with it absent. That is what non-uniqueness looks like from the inside, and Einstein was not the only one, or even the first to notice. Around 1920, Arthur Eddington, the same Eddington who organised the eclipse expedition that made Einstein famous, made the point explicitly. There is a standard way of generating the field equations. You write down a quantity called the action, built out of the curvature, and you vary it. The particular action Einstein used is built from something called the Ricci scalar. Eddington observed that you can perfectly well build an action out of the Ricci scalar squared instead. Do that, and you get equations that contain Einstein's plus extra terms. Nothing forbids it. It is not a fringe maneuver, it is a completely standard construction, and it was pointed out within 5 years of the theory's publication by one of the theory's own champions, and the field has known about it ever since. So the situation is this. There is a family of possible gravitational field equations. Einstein picked one member of the family because it reproduced Newton. Einstein himself later modified his pick. Eddington pointed out other members of the family immediately, and modern physics has continued to modify the equations whenever it needed to. Modified gravity models, extra terms, extra fields, entire industries of them. And this is where I want to introduce a pattern, because Mannheim states it in one sentence, and the sentence has stayed with me. You start out with the standard theory. It does not work for galaxies, so you invent dark matter. It does not work for cosmology, so you invent dark energy. It does not work as a quantum theory, so you invent string theory. Now, that is a provocative way to put it, and I want to give the other side its full weight before we go on, because the sentence is unfair if you leave it standing alone. Adding a new component when your theory falls short is not automatically a vice. It is often exactly right. Neptune was a new component. The neutrino was a new component, invented, essentially, to save the conservation of energy in radioactive decay, proposed by Pauli, who himself worried he had done something terrible, and confirmed a quarter-century later. Antimatter was a new component, forced out of Dirac's equation before anyone had seen a positron. The quark model was a new component. Physics is substantially a history of things being proposed to fix a discrepancy, and then turning out to be there. And dark matter specifically is not only a rotation curve patch, it does independent work. It helps explain how galaxies formed at all in the early universe. Ordinary matter alone struggles to clump fast enough. It shows up in the way clusters of galaxies bend light around themselves. It leaves a signature in the precise pattern of the leftover radiation from the early universe, and that pattern is measured to remarkable precision, and the standard model fits it very well. Dark matter is not one epicycle bolted onto one anomaly. It is load-bearing across a lot of cosmology. So the honest version of Mannheim's sentence is not that adding components is illegitimate. It is a question about the pattern. If a framework can absorb any discrepancy by adding one more unseen ingredient, then what would it ever look like for that framework to be wrong? At what point does a run of successful additions stop being evidence of a productive theory and start being evidence of a theory that cannot fail? There is no clean answer to that. Nobody has one. It is genuinely one of the hardest questions in the philosophy of science, and physicists mostly get on with the work instead of trying to settle it, which is probably correct. But it is the question this video is about, and it is worth naming now, while it is still abstract, so you recognize it later, when it stops being abstract and starts having numbers attached. Now, Mannheim's own position within that pattern is what makes him interesting rather than merely contrarian, because his response to the pattern is not to add a component of his own. His response is that he has not added anything at all. His account of his own career is that he took the theory and solved it, and followed where the solutions led, and did not invent a new ingredient at any point. Whether that is entirely true is something you can judge at the end, when you have seen what the theory actually requires. But it is the standard he holds himself to, and it is worth holding him to it. There is one more thing to say before we leave this, and it is about how the resistance works, because it is not what you would expect. The resistance is not really about evidence. Mannheim's experience, described plainly, is that everything he has written has eventually been published, but that getting it published puts a demand on his nervous system. He was already working on an alternative theory of gravity, which is difficult enough. Then, as we'll see, he also gave up a mathematical assumption at the foundation of quantum mechanics that nobody gives up. He describes taking flak from every direction at once, and his explanation for why questioning any part of general relativity is uniquely dangerous is not a claim about physics at all. It is a story about a room full of children. He gives talks to community groups sometimes, and he gave one to a middle school. He asked the room whether anybody could name a scientist. Every hand in the room went up, and every single one of them said the same name: Einstein. Then he asked whether anybody could name a second scientist. Total silence. He offers that as a warning about the hazards of appearing to challenge Einstein, and it works at that level. But I think it says something larger, and I want to leave it with you before we move on, because we are about to spend the rest of this video inside a very technical argument, and it is easy to lose the human shape of it. A field with exactly one saint is a field that has quietly decided which questions are askable. Not through any conspiracy, not through anybody's bad faith, simply because when one name becomes the whole public face of an entire subject, the parts of that subject become difficult to see separately. The equivalence principle and the field equations fuse into a single object called Einstein, and to poke at one is to be seen poking at all of it. And Mannheim's position, stated as carefully as he can state it, is that he is not challenging Einstein at all. Everything from the last part stands, the geodesic, the equivalence principle, general coordinate invariance, the metric as the gravitational field. He keeps all of it. He is looking at one specific step, taken for one specific reason, and asking whether it holds 1 billion times further out than the place it was tested. He puts it this way: you do not have to like what I have done, but you still have to address the issues I have raised. So let us go and address them. And to do that, we have to ask what a gravitational field equation would look like if it were not built to reproduce an answer we already had, if it were built instead the way we build every other force in nature. Part 6. The Universe. Where quantum theory came first. Here is a thought experiment, and it is the hinge of everything that follows. Imagine a version of the 20th century in which the order of discovery was reversed. Quantum mechanics arrives first. Quantum field theory gets developed. Physicists work out the theory of electricity and magnetism as a quantum theory, then the strong force that holds nuclei together, then the weak force that governs radioactive decay. All of that gets built, tested, confirmed. The whole edifice we now call the standard model of particle physics is standing, and gravity has not been done yet. Nobody has written general relativity. There is Newton's law, 300 years old, known to work in the solar system, and that is all. Now a physicist in that world sits down to build a theory of gravity. What do they write? They have a list of requirements, and it is the list from earlier. The physics must not depend on the observer's coordinates. The equivalence principle must hold. The metric is the gravitational field. Real curvature is where the Riemann tensor is non-zero. All of that they would derive exactly as Einstein did, because it is forced. But when they get to the field equations, the part that was not forced, they would not do what Einstein did. They would not reverse engineer from Newton. They would ask the question that every other force in their world had already answered. What makes a field theory work as a quantum theory? And the answer they would give, immediately and without hesitation, is that it has to be renormalizable. Let me explain what that means, because it is the technical heart of this, and it is not as forbidding as it sounds. When you take a classical field and quantize it, you run into an immediate accounting problem. A field is defined at every single point of space and time, not on a line, not on a grid, everywhere. Which means when you break it into modes, there are infinitely many of them. And when you switch on an interaction, so that the field can actually do something, every one of those infinite modes can get excited. You end up summing over an infinite number of contributions. The answer is infinity, which is not a measurement anyone has ever made. Renormalization is the procedure for handling that. The idea is that the parameters appearing in your original equations, the mass, the charge, are not the things you measure. What you measure is those parameters plus all the quantum corrections, so you redefine them, absorbing the infinities into the redefinition, and what comes out the other side is finite and agrees with experiment to absurd precision. Quantum electrodynamics predicts certain properties of the electron to something like 10 decimal places, and every one of those places has been confirmed. Feynman called the procedure dopey. Dirac disliked it his whole life, and described it as sweeping infinities under the rug. Both of them were expressing an aesthetic discomfort, and both of them used it, and it has become far more rigorous since the 1980s than it was when they were complaining about it. Mannheim does not think it is a trick. His comment on the subject is dry and I think telling. If we could get that trick to work for gravity, everybody would be delighted, because that is the problem. It does not work for gravity. In Einstein, gravity you can cancel the infinity at first order. Then it comes back at second order. You cancel it again, and it comes back at third, and you never catch up. There is no finite set of redefinitions that handles all of it. The theory is not renormalizable, and this has been known for a very long time, and it is the reason quantum gravity is hard. Every attempt to combine our two best theories of nature has run into this wall, and the great programs of the last 50 years, string theory, loop quantum gravity, are in large part responses to it. Now, why is quantum electrodynamics renormalizable and gravity not? There is a clean technical answer, and it comes down to a single property. Renormalizable theories have dimensionless coupling constants. The number that measures how strongly the force acts is a pure number with no units attached. In electromagnetism, that number is roughly 1 over 137, and it is famously just a number. Newton's gravitational constant is not a pure number, it carries dimensions, and that turns out to be exactly what breaks the renormalization procedure. Here is the part that should make you sit up, because it has happened before and it was fixed. The weak nuclear force was originally described by Enrico Fermi with a coupling constant that also carried dimensions, and that theory was also not renormalizable, and for exactly the same reason. Physicists spent years on it. The resolution was not to patch the Fermi theory. The resolution was to discover that it was not the fundamental description at all, that underneath it there was a gauge theory, with heavy particles called the W and the Z carrying the force, and that the Fermi theory was what that gauge theory looks like when you are working at energies well below the mass of those particles. The dimensionful constant was a low-energy artifact. Underneath, the theory was renormalizable all along. That is the precedent. A dimensionful coupling and a non-renormalizable theory turned out to mean not that the physics was broken, but that we were looking at the low-energy shadow of something with a different structure. So the physicist in our reversed history world writes down a renormalizable theory of gravity, gets a low-energy limit that reproduces Newton, and never introduces the Einstein field equations at any point. And this is not just Mannheim's private opinion. He notes that John Donoghue, who works on gravity as an effective field theory, agrees with him on this specific point. If quantum field theory had been developed before Einstein gravity, we would not have gone to that particular theory. We would have looked for a renormalizable field theory from the beginning, because that is what the strong, weak and electromagnetic interactions all turned out to be. Which brings me to a framing point that I think is the most quietly devastating thing in this entire argument, and it took me a while to see why. When physicists say quantum gravity, they do not mean find me a quantum theory of gravity. What they mean, in practice, in the actual daily work of the field, is find me a theory whose low-energy limit is Einstein. Those are different assignments. The first is an open question. The second has the answer written into the question. It assumes that the classical theory we already have is the correct target, and then goes looking for a quantum theory that lands on it. But we do not actually know that the classical theory is the correct target. We know it works in the solar system, we know it needs an invisible substance to work in galaxies, and we know it cannot be quantized, which is precisely the symptom you would expect if it were the low-energy shadow of something else, rather than the fundamental thing. Mannheim's version of the point runs deeper still. We always say classical physics is what you get when Planck's constant goes to zero, but Planck's constant never goes to zero. It is what it is. There is no switch. Classical behavior does not arise from the constant shrinking. It arises from interference effects washing out. So the whole historical direction, start with classical physics, then quantize it, is backwards relative to how nature is actually arranged. Nature is quantum, and classical physics is what quantum physics looks like from far away. Deriving the quantum theory by reverse engineering from a classical one is running the film backward and hoping it makes sense. His colleagues, he says, have taken the other approach. We already know the classical limit, and we are going to work it through. And his assessment of that program is delivered without any triumph at all. They have not succeeded is the best way to say it. He is careful to add that they have invested an enormous amount of thought into it. He is not sneering. Some of the most capable people alive have spent their careers on it. So here is where we have arrived. If you want a theory of gravity that can be a quantum theory, you need a dimensionless coupling constant. If you want a dimensionless coupling constant in a gravitational action, the arithmetic of derivatives forces your hand. You cannot get there with 2 derivatives of the metric, and you can get there with 4. And a 4-derivative theory automatically contains the linear potential we found back in part 4. Two completely independent lines of reasoning are now pointing at the same door. One came from galaxies, one came from quantum field theory. Neither knows about the other, but we still have not got a principle. Renormalizability is a requirement, not a derivation. It narrows the field without picking a winner, and there are several four-derivative theories you could write down. So what picks one? The answer is a symmetry, and it is a symmetry that was proposed in 1918, immediately dismissed for what looked like an unanswerable reason, and left sitting on the shelf for 40 years until a completely unrelated development in particle physics quietly removed the objection while nobody was thinking about gravity at all. Part 7. The Symmetry of Light. Imagine you're holding a triangle made of stiff wire. Now stretch it. Make it twice as big, 10 times as big, 1,000 times as big. Every angle stays exactly the same. The shape is preserved, only the size changed, and size in this operation is not a real property. It is a choice about how far apart you decided to hold your hands. That is conformal symmetry, roughly. A conformal transformation stretches or shrinks distances while leaving angles alone. And a theory with conformal symmetry is a theory in which the overall scale of things is not physically meaningful, a theory that has no built-in ruler. Now hang a small weight on one arm of your wire triangle and stretch it again. This time the arm sags, the angles change, the shape does not survive the stretching, because there is now something in the picture that knows how big things are. The weight has a mass, and a mass sets a scale, and once you have a scale, stretching is no longer a symmetry. It is a change. That single image is the entire history of this idea. Hermann Weyl proposed making conformal symmetry a local symmetry of physics around 1918, right on the heels of general relativity. And the objection came back immediately, and it seemed decisive. Things have mass. Electrons have mass. Protons have mass. You have mass. If mass breaks conformal symmetry, then conformal symmetry is not a symmetry of the world we live in, and the idea is dead. It stayed dead for 40 years. What killed the objection came from a completely different direction, and had nothing to do with gravity. In the 1960s, physicists working on the strong and weak interactions developed the idea of spontaneous symmetry breaking, the mechanism that gives rise to Goldstone bosons and eventually to the Higgs mechanism. And the lesson of that work, stated in the most general terms, is this: mass does not have to live in the equations, it can live in the vacuum. That distinction is worth slowing down for because it is genuinely strange, and it is the pivot of this whole part. We normally think of a particle's mass as a property of the particle, written into the fundamental description, the way a number is written into a formula. Spontaneous symmetry breaking says it does not have to be. You can have equations that are perfectly symmetric, with no mass appearing anywhere in them, and then a vacuum, an empty state, the lowest energy configuration of the universe. That is not symmetric. Particles moving through that vacuum acquire mass by interacting with it. The mass is a property of the state, not of the equations. It comes in through the back door. Think about a pencil balanced perfectly on its point. The situation is symmetric. There is no preferred direction. Let it fall, and it lands pointing somewhere. The direction it lands in was not in the physics. It was chosen when the system settled. The laws stayed symmetric. The state did not. So take your wire triangle and take the weight off the wire and hang it in the air around the wire instead. Now the triangle scales perfectly again, angles preserved, no sagging, and the weight is still there. It is just not part of the shape anymore. It belongs to the room. That is what makes conformal symmetry available again. A universe can have an exactly conformal underlying theory and still be full of massive particles, provided the mass is generated by the vacuum rather than written into the Lagrangian. Mannheim did not come to this from gravity. He came to it from particle physics, and this matters because it explains why he saw it at all. His first postdoctoral position was in Brussels with Robert Brute and François Englert, Englert being the one who shares the Nobel Prize for the mechanism that gives particles mass. They were many-body theorists, and their ideas came from condensed matter physics, from Philip Anderson's work on how photons effectively acquire mass inside a superconductor. At the same time, the renormalization group ideas of Kenneth Wilson and Leo Kadanoff were coming out of the study of phase transitions in materials and being translated into particle physics. So Mannheim was trained at the exact junction of two fields, and he asked a question that came directly out of that training. In a crystal at its critical point, the temperature where it transitions into an ordered phase. The correlations extend across the entire system. Every part of the crystal is coordinated with every other part. That long-range correlation is a scale symmetry. There is no characteristic length, because the characteristic length has become the whole crystal, and at exactly that point, the magnetization is still zero. The order has not appeared yet. What Wilson and the others found so exciting about this was that you could get long-range order out of short-range forces. You did not need a force reaching across the crystal to get behavior that spans the crystal. That was the great lesson of the Ising model. So Mannheim asked whether he could use the same trick to generate mass. Not at the critical point, at zero temperature, and he found a way to do it. A system sitting at what is called a fixed point of the renormalization group, where the coupling constant satisfies very specific conditions, and where the successive quantum corrections organize themselves so that their sum is finite instead of divergent. And he found the specific condition for mass to be generated dynamically. A certain quantity has to have its dimension drop by one whole unit, at which point the theory becomes so badly behaved at long wavelengths that it spontaneously reorganizes and long-range order appears and mass with it. That work was done long before he thought about gravity. It is why, when he later needed a conformal theory of gravity to contain massive particles, he already knew it could. Now let us go back to symmetry and count. The Lorentz group, the symmetry of special relativity, has 6 generators, 3 rotations and 3 boosts. Add the 4 ways of shifting your origin in space and time, the translations, and you have 10. That is the Poincaré group, and it is the symmetry group underlying essentially all of modern particle physics. Now add a dilatation, a uniform stretching, the thing we did to the wire triangle, that is 11. And it turns out there are 4 more transformations available, called special conformal transformations, and those 15 operations together close into a group, the conformal group. And here is the fact that gives all of this its weight. The conformal group is the full symmetry of the light cone. You can see why almost immediately. The light cone is the set of paths light can take, and it is defined by the condition that the space-time interval is 0. But if something is 0, then 25 times it is also 0. 1,000 times it is 0. Scaling does not disturb a null trajectory at all. Light does not care how big anything is, because light has no rest mass, and therefore carries no length scale with it. So the light cone has more symmetry than the Lorentz group. The Lorentz group is a subgroup of the full symmetry of light, and standard gravity gauges the Lorentz transformations and the translations locally, but leaves the conformal transformations alone. Make them local, and you get Weyl's theory. And here is where the constraint finally does its work. Requiring local conformal invariance does not leave you with a menu. It leaves you with exactly one action, the square of a quantity called the Weyl tensor, which is roughly the traceless part of the Riemann tensor, the part of the curvature that describes tidal stretching and squeezing rather than local compression. Count the derivatives. The Riemann tensor is 2 derivatives of the metric. Its square is 4. Integrate that over 4-dimensional spacetime, and the coefficient out front comes out dimensionless, which is exactly the property that makes a theory renormalizable. Look at what just happened. We asked for one symmetry, the symmetry of the light cone, made local. Out came a unique action. That unique action is 4th order, so it automatically contains the linear potential that could explain flat rotation curves, and its coupling constant is dimensionless, so it is renormalizable, which puts gravity on the same footing as the strong, weak and electromagnetic forces, instead of leaving it as the permanent exception. Nobody arranged that. Mannheim's motivation for going to conformal symmetry in the first place was neither of those things. It was the cosmological constant, which we will come to. The galaxy result and the quantum result both arrived unrequested. There is a second, entirely independent argument for the same action, and it is the one I find hardest to dismiss. Take the Dirac equation, the equation for an electron, and couple it to geometry through the spin connection, which is the standard way of describing how a spinning particle moves through curved space-time. Now do the path integral, integrate out the electron entirely, and see what is left behind in terms of the geometry alone. What is left is the Weyl squared action, and the reason is not mysterious. The Dirac action coupled to the spin connection was already conformally invariant, so when you remove the matter and keep the geometry, conformal invariance is what remains, and conformal invariance has only one action. The gravitational theory is generated by the matter we already know exists. You do not have to postulate it separately. Now, the price. Fourth-order equations of motion are, in Mannheim's own word, absolutely grotesque. Second-order equations are hard enough. Fourth-order equations in a curved four-dimensional geometry are objects of a different kind entirely, and there was a second price, much worse than ugliness, and everybody told him about it constantly. Fourth-order theories were known to contain something called a ghost, states with negative probability, which would make the theory physically meaningless. He did not know how to answer that. His response at the time was essentially to shrug at it and keep going. Let us see whether nature likes the theory, because if it does not, it does not, and if nature does like it, then nature will know how to solve the ghost problem even if I do not. That is either recklessness or faith, and it took 20 years to find out which. But first, somebody had to actually solve those grotesque equations, and in 1987, in a building in Maryland, 2 people sat down to try. Part 8. 4 months and 1 afternoon. In the late 1980s, Mannheim received a fellowship from the National Academy of Sciences and the National Research Council that sent him for a year to the Goddard Space Flight Center in Maryland, a branch of NASA. And there he met a man named Demos Kazanis. Kazanis was an astrophysicist, which Mannheim was not, and he knew relativity, which Mannheim needed. He had been a student of David Schramm at the Enrico Fermi Institute in Chicago before taking a position at NASA, and he had, some years earlier, done something remarkable that most people have never heard about. He had discovered inflation before Alan Guth. He had written a paper showing that if the early universe passed through a particular kind of exponential expansion, the horizon problem would disappear. Robert Brute and François Englert, working with Edgar Günzig, had shown the same thing independently at around the same time, the same Brute and Englert from Mannheim's Brussels postdoc, which tells you something about how small these circles are. Guth's paper came a little later, and what Guth added was the demonstration that the same mechanism also solves the flatness problem, which is why inflation carries his name. So these two sat down together in Maryland to solve the conformal gravity equations. 1987 into 1988. And here is the thing about that period that is difficult to convey now. Today, if you want the Weyl tensor for a given geometry, you open a computer algebra package and you ask for it, and it hands it to you in a second. In 1987, no such thing existed for this. There was no package you could open, there was nothing to ask, so they wrote their own, from scratch, using a program called Maxima. Picture the two of them at terminals in a NASA building, building an algebra engine capable of handling a fourth-order curvature tensor, entirely by hand, entirely from nothing, in order to find out whether an idea was worth anything. It took 4 months just to get the equations correct. Not to solve them, to write them down without an error in them. 4 months of work whose only output, at the end, would be a correct set of equations that might then turn out to be unsolvable, or might turn out to be solvable and give a completely wrong answer. And they did not know it would be 4 months. That is the part that stops me. They did not know the number going in. It could have been 8. It could have been 18. There was no way to estimate it because nobody had done it. They also did not know they would succeed at all. Mannheim's own summary of that period is understated to the point of comedy. You can see, he says, that Demos and I really believed this. We were going to invest 4 months in the future. 4 months of a career spent producing something that was not a result, on a theory that everybody they knew was telling them not to work on because it had a ghost in it. And then they had the equations right, and it took them 1 afternoon to solve them. I want to put you in that afternoon, because it is the pivot of this entire story, and it happened in a room with 2 people in it and nobody else knew. They are solving for the geometry outside a static, spherically symmetric source. In plain terms, what does gravity look like around an isolated round object? A star. This is the same question Karl Schwarzschild answered for Einstein's equations in 1916, while serving on the Russian front, and its answer is one of the most famous solutions in physics. They are looking for one thing first, and it is not exciting, it is survival. They need a 1 over the distance term. Because if you write down a theory of gravity that does not contain the Einstein-Hilbert action anywhere in it, then Newton is not guaranteed. Newton has to come out or the theory is finished on the spot. Any theory of gravity that cannot reproduce the falling of an apple is not a theory of gravity. The 1 over the distance term comes out. Mannheim describes being very, very excited about that, and you can hear why. That was the wall. That was the thing that could have ended it in the first hour of the afternoon, and it did not. And then, because the theory is fourth order and fourth order equations have more solutions than second order ones, there is a second term sitting there beside it, a potential that rises linearly with distance. They looked at it, and Mannheim says they almost fell through the floor. Because the arithmetic is instantaneous. It does not require any thought at all. If one term is falling with distance, and the other term is rising with distance, then somewhere in the middle, over some range, the sum of them is flat. Flat. That is the shape of a galactic rotation curve. That is the exact shape of the thing that nobody could explain. The thing that had required the invention of an invisible substance outweighing everything visible by 5 to 1. And it had just fallen out of a calculation that was not about galaxies at all. Nobody put it in. They were solving the exterior geometry of a spherical mass because that is the first thing you solve in any theory of gravity. The linear term appeared because the equations are fourth order, and the equations are fourth order because the action is the square of the Weyl tensor, and the action is the square of the Weyl tensor because they demanded local conformal invariance, which they demanded for reasons that had nothing to do with galaxies whatsoever. Now I want to make the logic of that flatness sharper, because there is a version of it that is much stronger than it first appears, and it took me a moment to see it. You might think a linear potential, a force that grows with distance, sounds like bad news, unphysical, run away. But look at what the observations actually require. The total orbital velocity in a galaxy is flat. That is measured. And the Newtonian contribution from the visible matter is falling. That is not in dispute either. It is what Kepler's laws demand from the mass you can see. So whatever is supplying the difference between the flat total and the falling Newtonian piece is not itself flat. It is rising. The missing piece has to grow with distance. That is not an assumption. It is what you get by subtracting one measured curve from another. And this is where the two candidate explanations stop being symmetric. Conformal gravity produces a rising term automatically, from the structure of the equations with nobody's permission. A dark matter halo has to be shaped by hand, with adjustable parameters, until it happens to produce a rising contribution of the right size in the right place. Because a halo made of ordinary gravitating particles does not naturally do that. It has to be arranged to. One theory hands you the shape, the other theory has to be tuned into it. Now, having got there, Mannheim and Casanas immediately noticed a consequence, and they wrote it into the paper they published in the Astrophysical Journal, and it is the thing that turns this from a modification of gravity into a claim about the universe. If linear potentials are important, they wrote, then the objects on the other side of the universe are putting out their own linear potentials, and those must be affecting local dynamics. Read that again, because it is the whole answer. A 1 over the distance potential dies away. It is local by construction. A distant galaxy contributes essentially nothing to the physics inside ours, because the fall-off has crushed it to nothing. A linear potential does not die away. It grows. So distant matter does not drop out of the calculation. It comes in. Which means that when you work out how a star moves at the edge of a spiral galaxy, you're not entitled to consider only that galaxy. You have to consider everything. And that is Mach's principle, the idea we met back in part 2, the one Mach used to explain why a spinning bucket knows it is spinning, the idea that local inertia is somehow determined by the distant matter of the universe. Einstein was deeply drawn to it, and it is often said to have motivated general relativity, but it does not survive there. It cannot. Einstein's geometry is asymptotically flat, which means that at great distance everything settles down to nothing, and the local system is cut off from the global one. Conformal gravity's geometry is not asymptotically flat. So the connection survives. Mach's principle comes back into gravity, 70 years later, through a term nobody was looking for. Mannheim's summary of what they had found is that there is an interaction between the local and the global physics, which sounds abstract until you realize what it is going to imply about where the missing mass is. Part 9. The missing mass was never missing. There is a second calculation that has to be done, and it is the one that closes the loop. We live in an expanding universe, but when you measure a galactic rotation curve, you are not measuring an expanding system. You are measuring the motion of stars and gas inside a galaxy, in the galaxy's own rest frame, in a structure that is gravitationally bound and is not expanding with the universe at all. So the question is, what does the expansion of the universe look like from inside a galaxy? Mannheim worked it through, and the answer, in this theory, is another linear potential, universal, identical in every galaxy, because it does not come from the galaxy, it comes from the cosmology. So now there are two of them, one linear potential generated locally by the visible matter inside the galaxy, one linear potential generated globally by the rest of the universe. Same functional form, same shape, two entirely different origins. It took him 7 years to untangle them. That detail deserves a moment. 7 years, not to have the idea, not to do the calculation, but to separate two terms that look identical in the data because they have the same dependence on distance. Two curves lying on top of each other, and you have to work out how much of the effect belongs to the galaxy and how much belongs to the universe, and there is nothing in the shape itself to tell you. There is one more piece. The cosmological linear potential strength is set by the curvature of the universe, specifically by the square root of minus the spatial curvature, which requires the universe to be negatively curved, a point we will return to. And the curvature of the universe has a characteristic scale, the Hubble scale, the size of the observable universe. So this extra potential comes out naturally at cosmological scale. It did not have to be forced there. Nobody dialed it in. It is the size it is because it is generated by the universe, and the universe is the size it is. And then there are fluctuations. The cosmological background is not perfectly smooth. Matter is clumped, there is structure, and those departures from smoothness contribute their own term. That one comes out quadratic, growing as the square of the distance rather than linearly, also universal, also nothing to do with the local galaxy. So the final structure of the gravitational potential inside a galaxy, in this theory, has 4 pieces. There is a local 1 over the distance term, which is Newton, which never went away. There is a local linear term, generated by the visible matter in that galaxy. There is a global linear term generated by the rest of the universe, and there is a global quadratic term generated by the lumpiness of the rest of the universe. Now let me say the thing this has all been building toward, and let me say it as plainly as Mannheim says it. The missing mass that we have defined as the dark matter problem is not missing. It is the rest of the visible universe, and it has been hiding in plain sight. It has been there all along. I want to sit here for a while, because I think this is the moment in the story that actually matters, and it is very easy to slide past it as just another technical claim. For half a century, the sky has been divided into 2 parts. There is the part you can see, every galaxy in every survey image, every catalogued object, the entire photographed universe. And there is the part you cannot see, the invisible part, and the invisible part was understood to be 5 times larger. That division has been the background assumption of essentially every conversation about the universe that any of us have grown up with. When you look up at night, you are looking at the minority. And this claim says, no, there is no invisible part. The pull that has been attributed to the dark halo is coming from the galaxies you can already see, from objects that have been photographed, catalogued, assigned numbers, and stored on hard drives at observatories all over the world for decades. Not exotic, not undiscovered, not dark in any sense whatsoever, just extremely far away and reaching in, because the potential that carries their influence grows with distance instead of dying with it. It has been there the whole time. That should land as something stranger than triumph. It is closer to the feeling of turning your house upside down looking for your keys and then finding them on the table in the middle of the room you started in. The keys were not hidden. The keys were never hidden. Something about the way you were looking made the table invisible, and the something, here, is a decision made about a differential equation before anyone had ever measured a galaxy's rotation. Because remember where the locality came from. It came from the 1 over the distance fall-off, and the 1 over the distance fall-off came from the second-order Poisson equation, and the second-order Poisson equation was chosen because it reproduced Newton, and Newton was extracted from the solar system. Once you have made that choice, you're locked in. If you're short of gravity in a galaxy, the missing gravity must come from inside that galaxy, because everything outside has been suppressed to irrelevance by the fall-off. There is no other option available to you. The halo is not really an empirical discovery. It is what the mathematics forces you to say once the fall-off is assumed, which means that the 2 competing pictures are not really arguing about whether there is enough mass in the universe. They agree about how much matter there is. They are arguing about how far a gravitational influence can reach. Standard gravity says, not far. Gravity is local, so put the mass where the problem is. Conformal gravity says, extremely far. The problem is not local, so you do not need new mass anywhere. Mannheim's own framing of why nobody took the second road is blunt and I think basically fair. You did not want to do it, he says, because you were hung up on 1 over r, and here is the sharpest form of it. With a 1 over the distance potential, if you have a gravitational problem in a particular place, you can only solve it by putting matter in that place. It is still local. With a linear potential, you can put matter outside and it can do the job. Now, I have been letting this run without resistance for a while and I should stop because there are objections and they are serious, and this video is not going to pretend otherwise. The first one is the obvious one. This sounds too easy. Any theory that lets distant matter contribute to local dynamics has just handed itself a very large adjustable knob. If everything in the universe can push on everything else, you can probably fit anything. That objection would be fatal if the theory had freedom in it. The test is whether it does, because a theory with a knob can fit 1 galaxy, and a theory with a knob can fit 10 galaxies, but a theory with a knob starts failing the moment you demand that the same setting work for all of them at once. The second objection is harder, and it is the one that matters most in the professional literature, and I want to put it on the table now rather than smuggling it in at the end. Rotation curves are the easiest thing for modified gravity to fit. They have been fitted successfully by more than one alternative theory. The hard evidence for dark matter is elsewhere, in the way clusters of galaxies bend light, in colliding clusters where the mass and the visible gas appear to have come apart, in the growth of structure across cosmic history, and in the precise pattern of the leftover radiation from the early universe. Any theory that removes dark matter owes an account of all of those. We will get to what conformal gravity does and does not have to say about them, and the answer in some cases is that it does not yet have one. But first, the fitting. Because a claim like this is not worth anything as an idea. It is only worth something if you can put it against real data from real galaxies and let it fail. And it very nearly did fail, not in the way anybody expected. Part 10. 138 galaxies and 200 points that refused. When Mannheim first applied the linear potential to real galaxies, there were 11 of them. 11. That was the entire population of galaxies whose rotation curves had been measured well enough that you could do serious modelling with them. That is where the observational situation stood when this began. The work of expanding that fell largely to a doctoral student named James O'Brien, whose thesis this became. Mannheim's instruction was straightforward. Go and find some galaxies for me, and we will see what they look like. O'Brien found 138 of them. Mannheim says he did not even know they existed, and that O'Brien found them all, 3,000 to 4,000 individual data points, across galaxies spanning orders of magnitude in luminosity and size, from faint dwarfs to bright spirals. Now, the fits. And I want to be precise about how they work, because the accounting is the entire argument. You fit each galaxy using its luminous matter only. No halo, nothing invisible. You take the light, you convert it to mass, and that is your source. Then you have the 2 universal potentials, the linear one from cosmology and the quadratic one from the fluctuations, plus one further universal parameter that comes from clusters of galaxies. Those are fixed, the same numbers for every galaxy in the sample. They are not adjusted from one galaxy to the next. They cannot be, because they represent the influence of the same universe on all of them. And then there is exactly one number you are allowed to choose per galaxy, the mass-to-light ratio of its visible matter, which is not a free invention. It is a real astrophysical quantity about how much mass a given amount of starlight corresponds to, and it has to come out in a physically sensible range, or you have not fitted anything, you have just written down a number. Now compare that to the alternative. A dark matter halo requires roughly 2 free parameters per galaxy. You have to specify how much dark matter there is and how it is distributed, and there is no theory that tells you those numbers in advance. They are fitted from the rotation curve you're trying to explain. 2 parameters times 138 galaxies is 276 additional free parameters, and crucially, none of those parameters is constrained by any other galaxy. Fitting galaxy number 40 tells you nothing about galaxy number 41. That is the difference, and it is a difference in kind rather than in degree. Mannheim's fits share their parameters across the entire sample, which means the theory had 138 independent opportunities to be caught out. Get the universal parameters right for the first 50 galaxies and wrong for the 51st, and it is over. You cannot go back and adjust because the adjustment would break the first 50. His own comment on this is the one I keep coming back to. We could so easily have failed. And then it did fail. Just not where anyone was looking. Here is the prediction that broke. The Newtonian term falls with distance. The linear term rises, which means that as you go further and further out from the centre of a galaxy, the rising term must eventually dominate. It has to. That is what rising means. So a flat rotation curve cannot stay flat forever. Eventually it has to turn upward, and there is a supporting observation that made this look right. In dwarf galaxies, small, faint, with very little visible mass, the Newtonian contribution is feeble, so the linear term wins early, and dwarf rotation curves are already rising. That is observed. It is one of the things the theory gets right without effort. The bright spirals are the ones where the turn-up should be delayed, because their Newtonian term is large and takes longer to be overtaken. So Mannheim expected to see the rise. He expected the bright spirals to bend upward at large radius. Then O'Brien's data came in. Go through it with them. There is a region, in each of these galaxies, where the theory says the curve must turn up. Go to that region and look at what the measurements do. They do not rise, not in one galaxy. Across the sample, roughly 200 data points sit in that awkward region, the place where the theory made a specific, unambiguous, falsifiable prediction. And every one of them curves the wrong way. They curve down. I want to hold you in that moment, because this is what it actually looks like when a theory is about to die. 20 years of work, 4 months of writing software, 7 years untangling two potentials, the 138 galaxies painstakingly assembled by a student, and in the exact region where the theory sticks its neck out furthest, the sky says no, 200 times over. The theory does not work. That is what Mannheim says happened. We applied the theory, and it does not work. And then the resolution, and it came from a term that had been sitting in the equations the whole time doing nothing dramatic. The quadratic potential, the one from the cosmological fluctuations, carries the opposite sign to the linear one. They push against each other, and the quadratic term grows faster, because it grows as the square of the distance. So at sufficient distance, the quadratic term does not merely compete with the linear one, it overwhelms it, and the total goes negative. Now think about what that total is. It is a velocity squared. A velocity squared cannot be negative, because a velocity cannot be an imaginary number. There is no such thing as a star orbiting at the square root of minus something. So the equations are not producing a wrong answer at large radius. They are producing no answer. Past a certain distance, there is simply no orbit available. Nothing can be bound out there, which means the galaxy has to end. Conformal gravity predicts that galaxies have a finite size, and that is a genuinely different kind of statement from anything the standard picture offers, and it is worth being clear about why. A 1 over the distance potential never cuts off. Whatever else you want to say about Newtonian gravity, it goes on forever. It gets weaker and weaker, and it never reaches zero, so no matter how far from a galaxy you place an object, there is always formally a bound orbit available to it. Newtonian gravity has no way of telling you where a galaxy stops. Neither does a dark matter halo, whose outer edge is set by how you chose to model it. Here you get an actual physical reason for a galaxy to have an outer boundary. The competition between two terms with opposite signs runs out of room. The failed prediction produced a sharper claim than the theory had before it failed. That does not happen very often, and when it does happen, it is usually a sign that something real is being described, because a theory with enough freedom to be tuned would simply have been tuned and would never have produced the wrong prediction in the first place. And there is one more thing in the data, and it may be the single most important observational fact in this entire story, and it belongs to nobody. Take each of the 138 galaxies and compute one quantity, the orbital velocity squared, divided by the speed of light squared, divided by the radius. That combination has units of 1 over a length. It is a characteristic inverse length for that galaxy. Do it for every galaxy in the sample, dwarfs, bright spirals, everything, and you get the same answer, something like 10 to the power of minus 30.5 per centimetre. All of them. And that number is approximately the inverse of the Hubble radius, the size of the observable universe. A cosmological quantity is sitting inside individual galaxies, in the measured data, in every one of them, regardless of how big or bright or faint they are. Now, this is not a feature of conformal gravity, and Mannheim is emphatic about that. It is written on the data. It has nothing to do with him. It is the same universal acceleration scale that Mordechai Milgram identified in 1983 when he proposed MOND, modified Newtonian dynamics, where it appears as a constant he called a naught. It is the same scale that appears in John Moffat's alternative theory, which uses a logarithmic potential and arrives at the same universal acceleration from a different direction. 3 people, 3 completely different theories, 3 independent routes, and the same number falls out of the observations for all of them, because it was in the observations before any of them arrived. And that produces the challenge Mannheim has been putting to his colleagues for decades, and it is not rhetorical. If the Standard Model is correct, then the Standard Model has to explain why there is a universal acceleration of order, the inverse Hubble radius appearing in every galaxy in the sky. Where does it come from? Why is a property of the whole universe stamped into the rotation of individual galaxies, each of which formed separately at different times with different histories? Derive it, he says. If you do not like our formula, derive it in your theory. Because it fits the data points, and the data are saying that there is a structure there which is currently being missed. That challenge has not been answered. It also has not stopped anyone, because the Standard Model is doing a great deal of other work very successfully, which leaves conformal gravity where it has been for most of its existence, fitting the galaxies, unable to be dismissed on the galaxies, and blocked from serious consideration by something that had nothing to do with astronomy at all. The Ghost. Part 11. The Ghost. For 20 years, every physicist Mannheim spoke to told him the same thing, and they were not being unkind. They were telling him something that everybody knew. The theory has a ghost. It has states of negative norm. It is not unitary. It is not physical. It cannot be allowed. Let me explain what that actually means, because the word ghost sounds like jargon, and the underlying problem is not. In quantum mechanics, you calculate probabilities, and probabilities have a hard requirement attached to them. They must be positive, and they must add up to 1. Something has to happen. That requirement is called unitarity, and it is not a nice feature of quantum mechanics. It is the thing that makes quantum mechanics mean anything at all. A theory that predicts a negative probability is not a theory that is slightly wrong. It is a theory that is not saying anything, and fourth-order derivative theories were known to produce exactly that. Negative norm states, ghosts, which translate directly into negative probabilities. Here is where it comes from, and you can see it in the propagator, which is the mathematical object describing how a disturbance travels through the field. In a theory with both second-order and fourth-order pieces, the propagator is a difference of 2 terms, 1 over a certain quantity, minus 1 over that quantity shifted by a mass. That minus sign is the whole problem, and it is also the whole point. It is the point because each of those 2 terms individually falls off slowly at high momentum, but the difference between them falls off much faster, fast enough that the infinities are tamed. The minus sign is precisely what buys you renormalizability. It is why the theory can be a quantum theory at all, and it is the problem because if you insert a complete set of intermediate states into that expression, in the standard way, the minus sign appears to require a set of states with negative norm, negative probability, ghosts. So the theory appeared to be paying for its one great advantage with its own destruction. The thing that made it renormalizable was the thing that made it meaningless. This is not a new problem either, and its history is a roll call. Paul Dirac tried to handle the infinities of quantum field theory using something called an indefinite metric, which has this same character. Wolfgang Pauli picked up the idea and it led him to the Pauli-Villard regulator, which is a difference of 2 propagators, and which does successfully preserve gauge invariance during renormalization, and which carries the same troubling minus sign. Werner Heisenberg's nonlinear spinor theory in the 1950s had an indefinite metric in it too. T.D. Lee introduced a model in the 1950s that let you calculate the renormalized coupling constant in closed form, which was very powerful, and which in a certain range of parameters suddenly produced negative norms. Pauli, Gunnar Kellen, Lee and Heisenberg all worried at that problem. None of them solved it. Mannheim had actually bumped into this as a graduate student, looking at Heisenberg's theory. He knew the problem was old. He did not know what to do about it, and he said so. The answer came from somewhere nobody was looking, and it came from a man named Carl Bender. In 1998, Bender and his former student Stefan Betcher were studying a Hamiltonian. And this Hamiltonian was, on its face, absurd. It was momentum squared plus E times position cubed, with an explicit imaginary number in the potential. Now, in ordinary quantum mechanics, the Hamiltonian must be Hermitian, and Hermiticity guarantees that the energies come out real, which they must because energy is something you measure. A Hamiltonian with an imaginary number sitting in the potential is not Hermitian. You would bet anything you own that its energies come out complex, which would make it physically meaningless. Every one of its energies is real. Bender and Betcher showed it by approximation. A few years later, Patrick Dorey, Claire Dunning and Roberto Tateo proved it as a rigorous theorem. There is no wiggle room in it. The eigenvalues of that manifestly complex Hamiltonian are, without exception, real numbers. The reason is a symmetry called PT. Parity reverses space, so position cubed flips sign. Time reversal flips the sign of the imaginary unit. Do both, and the imaginary term is left exactly as it was. The Hamiltonian is invariant under the combination of the two, even though it is not Hermitian. And the deeper principle underneath that goes back to Eugene Wigner in 1960. When Wigner worked out how time reversal has to operate in quantum mechanics, he noticed something about the Schrödinger equation. It contains an explicit imaginary unit. So if you reverse the direction of time, you only preserve the equation if the imaginary unit also flips sign, which requires an operator that conjugates numbers, not functions. That kind of operator is called antilinear, and here is Mannheim's contribution, and it is the one that reframes the whole subject. If a Hamiltonian has an antilinear symmetry, then that symmetry turns any energy into its complex conjugate. So for every energy the system has, its conjugate must also be an energy, which leaves exactly two possibilities, and only two. Either an energy equals its own conjugate, meaning it is real, or the energies come in complex conjugate pairs. So hermiticity is sufficient for real energies. It is not necessary. What is necessary is an antilinear symmetry. You will not find that in a linear algebra textbook, and Mannheim points out exactly why. It is not a linear condition. The whole subject of Hermitian operators was set up by people asking a linear question, and the necessary condition lives outside the frame they built. There is a second half, and it is the one that kills the ghost. Bender realized that when a Hamiltonian is not Hermitian, you are not entitled to construct probabilities the standard way. Dirac's recipe is to take a state, take its Hermitian conjugate and multiply. If the Hamiltonian is not Hermitian, the correct partner state is not the Hermitian conjugate, it is the PT conjugate, and when you compute the norm that way, it comes out positive. Read that again, because it is not a repair. When people said the theory had a negative norm, what they had actually done was apply Dirac's formula in a situation where Dirac's formula does not apply. They were computing in the wrong space. The negative number was real, but it was not a property of the theory. It was a property of the arithmetic they had chosen. Now, the meeting. 2008, a conference in Fort Lauderdale, run by the University of Miami. Mannheim has known Bender for many years. Bender gives a talk about the Lie model, that 50-year-old problem with the negative norms that Pauli and Heisenberg had failed to fix, and shows that when you use the PT construction, the ghost disappears and the model is perfectly consistent. Mannheim is sitting in that audience having spent 2 decades being told his theory has a ghost, and afterwards he goes up to him and says, essentially, you have a way to get rid of a ghost and I have a theory with a ghost. Let us get together. Bender was at Los Alamos for the year. Mannheim went there. They sat down. They solved it in 3 days. Mannheim is careful about that number when he tells it, and I think the care is the most human thing in this entire story. It may be 3 days, he says, but we both came with 20 years of prior experience. 2 men walked into a room in New Mexico carrying 20 years each of work that had not paid off, and the 2 halves fitted together in 72 hours. The result was published in Physical Review Letters in 2008. What they showed, technically, was that the 4th-order derivative oscillator, the model that describes the quantum mechanical limit of conformal gravity, has no ghost. And the key, which came partly out of earlier work Mannheim had done with Aaron Davidson at Ben-Gurion University, was that the offending states are not normalizable. Everyone had assumed they were. When you insert a complete set of states into that propagator, you are presupposing that those states can be normalized, and if they can, the negative norm conclusion follows. They cannot. Bender had already built an apparatus for handling states like that. You continue them into the complex plane. Something that blows up along the real axis behaves perfectly well along the imaginary one. The theory lives on the imaginary axis, and everyone attempting quantum gravity, Mannheim observes, was doing it entirely on the real axis, which is, in his opinion, why they could not succeed. Now I want to underline the shape of what happened, because it is unusual, and it is easy to misdescribe. They did not get rid of the ghost, they never got rid of the ghost. What they showed was that the reasoning which caused you to think there was a ghost was not valid. Everybody else working on this had been adding terms to their theories to cancel the ghost. Extra fields, extra structure, whole mechanisms designed to kill the thing. And none of that was ever necessary because there was nothing to kill. And there is an argument that it could never have been there in the first place. And this one is my favourite thing in the entire theory, because it is so short. Take the Dirac action for a fermion coupled to geometry through the spin connection. The ordinary standard description of how an electron moves through curved spacetime. Integrate out the fermions. What is left is the Weyl-squared action, as we saw earlier. Now, the standard model of particle physics does not have a ghost. We are certain of this. It is the most tested theory in the history of science. So if the gravitational theory generated by integrating out standard model fermions had a ghost, then the entire standard model would collapse the moment you coupled it to gravity. Every prediction, everything at the Large Hadron Collider, everything. Which leaves exactly two options. Either there is no ghost in conformal gravity, or the standard model of particle physics is wrong. There is a broader claim underneath all of this that Mannheim states as the summary of his whole program, and it is a strange thing to hear said about quantum mechanics after 100 years. The essential feature of quantum mechanics, he says, is not hermeticity. It is probability conservation. Hermeticity implies probability conservation. Probability conservation does not imply hermeticity, in exactly the same way that hermeticity implies real energies, while real energies do not imply hermeticity. We took a sufficient condition and treated it as the definition, because Dirac inherited it from 19th century work on differential equations, where it meant something quite specific and technical about surface terms. Physics, as Mannheim puts it, is richer than that. Quantum mechanics is richer than that. The set of states you use to compute probabilities does not have to be the Hermitian conjugate of the states you started with, and once you allow that, a whole run of old puzzles unlocks, including one that had bothered him since he was a student, which is that the theorem used to explain why a particle and its antiparticle have the same lifetime requires a Hermitian Hamiltonian, and a Hermitian Hamiltonian has no complex energies, and without complex energies neither particle would decay at all. The theorem was being applied to the one situation it excluded. So by 2008, the last technical barrier is down. The theory is renormalizable, it fits the galaxies, it does not have a ghost, and now we have to talk about what it costs. Part 12. What it costs, what it owes, and what it means. If you take this theory seriously, several things you were taught about the universe stop being true. Let me go through them, and then I am going to turn around and take most of it away again, because that is what honesty requires here. There was no Big Bang, not in the sense of no beginning to the expansion, in the sense of no initial singularity. Here is why. The standard equation governing the expanding universe has the energy density on one side, and that density grows without limit as the universe shrinks. Run the film backward and everything blows up. Infinite density, infinite curvature, a point where the equations stop being able to say anything. That is the singularity, and it is also the origin of the flatness problem, because at that moment the curvature term becomes utterly irrelevant compared to the density, and getting a universe as flat as ours out of that requires extraordinary fine-tuning at the start. Inflation was invented to fix exactly this. In conformal gravity the sign is reversed. That density term comes in with a minus instead of a plus, and with the sign reversed, the equation never blows up. There is no moment of infinite density. Run the film backward, and the universe does not shrink to a point. It reaches a finite minimum size, and that is all. The flatness problem is solved not by a mechanism, but by there never having been a problem. So there is no inflation either. And the horizon problem, the puzzle of why opposite sides of the sky have the same temperature when they should never have been in contact, also disappears without it. Whether a horizon exists depends on how the expansion behaves at early times, and exponential expansion is not the only behavior that removes it. Anything expanding fast enough will do. You do not need inflation to solve the horizon problem, and in this theory you do not need it to solve the flatness problem either, and the acceleration of the universe comes for free. A negatively curved space acts like a concave lens. A convex lens converges light, a concave one spreads it. So if the universe has negative curvature, light is pushed apart by the geometry itself. No dark energy component required. Mannheim had written this down in 1992 and not pursued it, and when the accelerating universe was announced in 1998, he applied it immediately and got a fit that lies on top of the supernova data. And here is the part that makes it a real prediction rather than an accommodation. Because the various contributions to the universe's energy budget have to add to 1, and because the curvature term is positive in this theory, the deceleration parameter is boxed in. It has to lie between 0 and -1. There is no freedom in that. If the data put it anywhere else, the theory is dead. The fit gives about -0.37, which is inside the window, and there is no graviton. Asked directly whether the graviton is composite or fundamental, Mannheim's answer is neither. It does not exist. There is a theorem of Steven Weinberg's requiring that a spin-2 particle must couple through the Einstein tensor, which would rule this theory out. But the theorem has a condition attached. It assumes the space of states has a positive definite structure. In the fourth-order theory, the graviton comes out with 0 norm, not negative, 0. So gravitational radiation exists because this is a covariant metric theory, and gravitational waves are exactly what such theories produce, and we have detected them from colliding black holes, and that detection stands. But when you quantize that radiation, you do not get an observable particle out the other end. The graviton is not there to be found. And then a speculation, which Mannheim flags as speculation the moment he says it, and which I will flag twice as hard. It is possible, he says, that the collapse of the wave function is caused by the emission of these unobservable zero-norm gravitons. He notes he has written it down, so he will say it, and that this is about as far as he has taken it. That is not a result. It is a physicist's late-career intuition about the oldest unsolved problem in quantum mechanics, and it should be held loosely. Now, everything I have just said is what the theory gives you if it is right. Here is what it owes. The fluctuations are not done. The tiny variations in the leftover radiation from the early universe, the pattern that cosmologists measure with extraordinary precision, and that the standard model with its 0.3 and 0.7 fits remarkably well, have not been shown to work in conformal gravity. Neither has the growth of large-scale structure. Mannheim states this himself, without qualification. He has been working on the fluctuations with a series of students. He does not know whether it will work, and anyone who withholds judgment until the fluctuations are fitted is fully justified in doing so. His own words are that without them, he has a theory of nothing rather than a theory of everything. That is not a small caveat. That is the largest single body of cosmological evidence unaddressed. Gravitational lensing by clusters of galaxies is also unresolved, and Mannheim is clear about why it is harder than it looks. The standard lensing formula assumes light arriving from an asymptotically flat geometry. In a theory with a linear potential, the geometry is not asymptotically flat, and the whole calculation has to be redone from scratch, and there is a live dispute in the literature about how to do it correctly. He draws a distinction I found genuinely useful. Bending of light by the sun is a difference measurement. You observe a star's position with the sun out of the way, and then with the sun in the way, and everything happening far from the sun is common to both and cancels out. You cannot move a galaxy cluster out of the way. Cluster lensing measures the entire trajectory, so the two cases are not equivalent, and a theory can handle one without automatically handling the other, and there is evidence he does not raise that any account like this has to face. In colliding clusters of galaxies, the bullet cluster is the famous one, the hot gas, which is most of the ordinary matter, gets slowed down in the collision while the gravitational mass, measured by how the system bends light, sails straight through and ends up somewhere else entirely. Mass and visible matter come apart in space. That is very hard for any theory in which gravity is generated by the visible matter alone, and it is widely regarded as the single strongest result against pure modified gravity. And there is a published technical objection. In 2013, a paper in Physical Review D argued that Mannheim's potential does not reduce to Newtonian gravity at short distances unless you assume unphysical behavior in the mass density of the proton, which would put the theory in conflict with laboratory experiments that have measured gravity at small scales and found no deviation from Newton. A related claim was that for a source with positive total mass, The linear potential comes out with the wrong sign, negative, when fitting rotation curves requires it positive. Mannheim published a reply, arguing that those results follow only from treating gravitational sources exactly as standard gravity treats them, which violates the theory's own conformal invariance and so does not apply to it. The exchange went back and forth through comments and replies in the same journal. That is not settled. I am not going to pretend to settle it for you. What I will say is that it is a real, specific, technical objection in a peer-reviewed journal, and it is the kind of thing that decides these questions, and it has not been decided. And there are the ordinary unfinished pieces. The right-handed neutrinos this theory requires cannot serve as dark matter. Mannheim has only lower bounds on their mass, and those bounds are out of reach of the Large Hadron Collider, and a dark matter neutrino would need to be far lighter. He has not explained why gravity is roughly 40 orders of magnitude weaker than the electric force. Asked about Dirac's large numbers hypothesis, he simply said he did not know enough to answer, which is a rarer sentence in physics than it should be. So where does that leave us? Look back at the pattern from part 5. It does not work for galaxies, so you invent dark matter. It does not work for cosmology, so you invent dark energy. It does not work as a quantum theory, so you invent string theory. That sentence entered this video as a criticism of the standard model, but run it against conformal gravity now. The fluctuations do not work yet. The cluster lensing does not work yet. The bullet cluster is unanswered. And a critic says the Newtonian limit fails at short distances, and the reply is that the critic applied the wrong kind of source. I am not saying those are equivalent. The scales are different and the track records are different. What I am saying is that the pattern is not a disease that one side has and the other does not. It is what it looks like from the inside when a theory meets data that does not fit it. Everybody patches. The question of when patching becomes pathology has no clean answer, and anyone who tells you it does is selling something. Which brings us back to the question this whole video has been holding open. Is the dark matter illusion about to collapse? And why would that be frightening? Here is the answer, as plainly as I can give it. The illusion is not dark matter. Dark matter may well be real. A great deal of very good evidence points that way, and the searches continue, and finding it would be one of the great moments in the history of science. The illusion is the belief that fitting the universe and explaining it are the same act. That is what this entire story is actually about. Einstein's field equations were built to reproduce a result we already had, in a region we had already measured. They succeeded, and were then applied 1 billion times further out. Where they fell short, we added an ingredient. Where they fell short again, another. Each addition was reasonable. Each was made by serious people for serious reasons. And together they have produced a picture in which 95% of everything is composed of things no one has ever detected, and in which every galaxy in the sky carries a number stamped into its rotation that nobody can derive. That is the frightening thing. Not that there might be no dark matter, that a science could spend 40 years and a generation of careers and billions of dollars in detectors a kilometre underground and not be able to tell from the inside whether it was measuring the universe or measuring its own assumptions. And nothing in this story gets to be settled by elegance. Conformal gravity is beautiful. One symmetry, one action, no adjustable structure, 138 galaxies fitted with parameters that are shared rather than tuned. It is also possibly wrong, in ways that would show up in the fluctuations its own author has not finished calculating. Mannheim tells his students 2 things. The first is not to trust experts, and he backs it with Wigner's definition of an expert as the person who has made the most mistakes in the field. The second is the one that closes this. The number of beautiful mathematical theories, he says, exceeds the number of physically relevant ones by an enormous margin. So do not be seduced by the mathematics. Mathematics will take you a long way, and it is the language we have, and we could not do any of this without it. But you must never lose sight of the data. Nature will keep you honest. And the thing about that sentence, the reason it is the right place to end, is that it does not take a side. It is not a weapon for the alternative theory, and it is not a defense of the standard one. It cuts in every direction at once, including at the man who said it. Somewhere out there, in the fluctuations of the early universe, or in the way a cluster of galaxies bends the light passing through it, or in a detector a kilometre under a mountain waiting for a single nucleus to move, the answer already exists. It has existed the entire time. It is not waiting for anyone's permission, and it does not care whose career depends on it. We just have not read it yet. And the strangest thought to fall asleep on tonight is not that a quarter of the universe might be missing. It is that it might not be missing at all. That everything that has ever existed might already be up there, catalogued and photographed and stored on hard drives in observatories all over the world, in the images we have been looking at for 100 years, hiding in plain sight, there the whole time,